Good morning, students. In strength of material, today we're going to see about the unit 3. Unit 3 title will be stresses in the beam. So stresses in the beam unit has been comprised into two portions. One will be that the beam has been subjected to bending that creates bending stress in a beam. The second half will be deals with the shear stress. If you are applying this shear load, it creates a shear stress variations. So the variation for the bending as well as shear has been calculated, and the variation has been drawn as per the cross section for the beam subjected to a bending load. It creates bending stress. The variation will be a linear variation. It is irrespective to the shape. If the shape may be rectangular, or it may be a circular, or it may be a square, or I section or T section, whatever may be the cross section is getting varied, the bending stress variation will be always tends to remain in the uniformly varying triangular shape. So the second half deals with the shear stress. The shear stress variation has been varied according to the cross section of the member. So the cross section of the member will be of different shape. If it is a circular, the shear stress variation will be along the different shape. If it is a rectangular, as well as circular, T section, square, followed by I section, T section. So if the section is getting varied, the shape of the shear stress has been get varied. So the variation will be represented in the diagrammatic representation. With the help of this data, we will accumulate, we can easily calculate that what are the type of stresses that has been occurred in a member, and next will be where the bending moment variations will be higher, and where the shear stress variations will be higher. So all the data has been easily acquired from the help of the calculation work. So we'll gone through all the calculations of work one by one. So first thing will be that theories of uh, in order to calculate the bending stress variation, we are applying the theory of simple bending. The theory of simple bending has been give the justified diagrammatic representation of bending stress variation. So in that uh, theory of bending stress, that is simple bending equation has been occurred from certain basic assumptions, that the assumptions indicates that the material is homogeneous and the material is isotropic and it obeys the Hooke's law. So in order to obtain the relationship, we are taking a purely homogeneous material. Homogeneous material is nothing but it should be it is a composition of uniform only one material. Next will be isotropic, which it is subjected to an isotropic property, and it should obeys the Hooke's law. Hooke's law is nothing but the stress and strain should be directly proportional up to the elastic limit. So it should satisfies all these conditions. Next assumption will be that the transverse section which are plane before bending remains plane after bending. So as per the theory, it states that if you are applying the load, the member will tendence to an variation, a triangular variation. That after removing the load, the member will transform into its original position along with its variation, and the bending will be in the uniform nature before and after applying of load. Next will be the radius of curvature is very large to the cross section of the beam. So the bending of the beam has been occurred, and the radius of curvature has been keep on increasing due to that. So next will be each layer of the beam is free to expand or contract. So the beam is comprises of n number of layers, and it has been altogetherly performed as an uniform member. So altogether uniform member will be represented as a beam. So the beam has been freely tends to expand and contract. So within the elastic limit, so it is performance will be that elastic level. So next will be that we will as per the assumptions we has been derived the equation. That equation is nothing but m by I equal to E by R equal to sigma B by Y, which is a very simplest formula. With help of these relations we can able to calculate the bending stress. So m is nothing but moment, I is the moment of inertia, and E is the Young's modulus, followed by R is the radius of curvature. Next, sigma B is bending stress. Y is the distance from the bending stress of the member to the bending stress of the member to the neutral axis. So these are the formulas which helpful for the variations of a member along with its property. With help of this valuable equation, we will find out the bending stress for any type of cross sections and for any different combinations of loading subjected to the cross sections. So this formula will be the base parameter formula for to calculate the moment of resistance of a member along with its bending stress and the moment of inertia, that is load carrying capacity, as well as moment that is load carrying capacity of a member. So all the parameters totally incorporated into an equation, that is m by I equal to E by R equal to sigma B by Y. So next, in order to obtain the section modulus, because section modulus is most important, the steels are for a design of steel member, we will calculate the moment of inertia, that is moment of inertia along with its section modulus, because section modulus is the value that indicates that how much quantity of steel to be arrived and steel to be utilized in the member. So for that purpose we have to be very clear that clear about the section modulus, because section modulus is the most important prominent for steel as well as for a concrete members, concrete column or beam, or it may be of any cross-sectional shape. So the sectional value will be represented by a form, that is represented by a term Z. So Z value will get varies with respect to its cross section. So we know that a well-known formula from the theory of simple bending, the formula will be m by I equal to sigma B by Y. So m equal to sigma B into I by Y. So by making rearrangements, we are finding that moment of inertia to the distance from the neutral axis of the member will be section modulus. Section modulus is that equal to I by Y. Next, with the help of an representation, we has been easily calculate the moment of resistance. Moment of resistance equal to sigma B into Z. So sigma B is nothing but bending stress and Z is nothing but sectional modulus or modulus of section. So the values will get differ for a cross sections. So the cross sections will vary. The moment of inertia value will also get vary. Similarly, the sectional modulus value will also gets vary according to the situations. So we will go through the cross-sectional values, moment of inertia, and the sectional modulus for the different cross sections, uniformly varying cross sections. First, we will go through that regular section, that is a rectangular section. That is, if it is a rectangular section, the it has a cross section of B will be the breadth and D will be the depth. That Y value will be directly calculated. That is, half of the depth will be the Y value, and the moment of inertia I value will be B dq by 12. Next, the section modulus Z will be can be obtained by the relationship of Z equal to I by Y. From that relationship, we will acquire the formula as a BD square by 6. Next will be for a I section. For the I section, the total breadth will be capital B, and the in between depth between the flanges will be small d. So in order to calculate that y value, that is total depth by half of the total depth, that is d by 2. Next will be moment of inertia is capital B into d cube minus bd cube by 12. Next z value will be bd cube minus 6bd cube, that is bd cube by 6d. So this will be the formulas for an I section. Next we will go through the formula for a regular circular section. The circular section which has a diameter of capital D. So D equal to, that is y equal to d by 2, half of the diameter, followed by moment of inertia equal to pi by 6 pi d power 4 by 64, z equal to pi d cube by 32. So these are the standard formulas for moment of inertia as well as the sectional modulus for the circular sections. So next we will go through the formula for a hollow section. In order to calculate the y value for the hollow section will be d by 2. For the moment of inertia value for the I section will be pi by, that is pi by 64 into capital D power 4 minus small d power 4. That will be the moment of inertia value. Next will be sectional modulus equal to pi by 32 into capital D power 4 minus small d power 4 divided by d. So that will be the formula to calculate the moment of inertia for a hollow sections. Next, we will go through the moment of inertia for a triangular sections. So the triangular sections of dimensions will be height of the triangular member will be h and base will be b. So if you are calculating the moment of inertia from the base of the circle will be 1 by 3. From base, from the apex it will be 2 by 3. So the moment of inertia value will be bhq by 12, or else from the apex it is bhq by 36. The moment of inertia value for the members has been calculated. Next we will go through the sectional modulus value. Sectional modulus value will be bhq by 4. So these are the standard formulas for the moment of inertia as well as sectional modulus for different format of cross sections. So the cross section will varies occur. If the cross section has been getting varied according to the situations, the moment of inertia value followed by sectional modulus value will also get varied according to the situations. So the next will be that if the situations has been getting differs, that cross sectional member will also will differ, and the loading capacity will also get differs. If the loading capacity values has been differed, then the moment value will also get differed. Next will be followed by the if the cross section has been get varied, the sectional modulus value will also gets varied. So if the altogetherly the varying parameters has been incorporated into a single formula with the help of theory of simple bending. The theory of simple bending is nothing but m by I equal to sigma b by y. So that formula will be very much utilized to calculate the bending stress variations. So we will go through one sum that will be easily helpful in order to identify how much bending variation has been occurred in the member. So for that we will go through one sum. A simply supported beam which is having a rectangular section of size for 60 by 35 mm and 3 meter long, carrying a load of 5 kilonewton at midspan, determining the maximum bending stress induced in the beam. So next will be that with the help of this given question, we will draw this diagrammatic simply supported beam, which is supported at both ends, RA as well as RC. The load 5 kilonewton, which is at mid span. The total span will be 3 meters. So half of the span will be 1.5. So we has been drawn the simply supported beam with the point load, which has a cross section of breadth value will be 60 mm and height value will be 35 mm and length will be 3 meter, followed by the load equal to 5 kilonewton. So these are the data which has been given in the question. So we want to find the bending stress in the beam. So in order to calculate the bending stress in the beam, we know the equation that the bending stress equation is that sigma B equal to M by I into Y. So we want to manually calculate the three values: moment value, inertia value, and Y. So we will calculate the values one by one. First will be we calculate the moment value. So in order to calculate the moment value, we want to calculate the reaction. So first thing we are, in order to calculate the reaction, we are taking moment about A point. So moment about A point. So the RC member will be travel in this direction to reach the A point. So RC into 3, that 5 kilonewton will be travel in this member to reach the A point. So 5 into 1.5. So from this value, we has been calculated RC equal to 2.5 kilonewton by applying the vertical condition, equilibrium vertical condition, summation V equal to 0. We has been calculated RA plus RC equal to 5 kilonewton. From this, we has been previously calculated RC equal to 2.5 kilonewton. So RA equal to 5 minus 2.5. RA equal to 2.5 kilonewton. So we has been calculated the reaction values for RA as well as RC will be equal to 2.5 kilonewtons. So next we are taking moment about the B point, because B point will have the maximum bending moment. So B point will have the maximum bending moment. So the maximum bending moment will be calculated at a point of B. So we will transform all the points to the B point. So for that, we has been transforming the reaction to the B points, so RC into 1.5. So RC value is 2.5 into 1.5. We has been obtained the moment value as a 3.75 kilonewton meter. We know that 1 kilo has been transformed into 10 power 3, followed by moment will be transformed into 10 power 3 in order to convert it as a mm. So the moment equal to 3.75 into 10 power 6 Newton mm. So we has been calculated the moment value. Next, we will calculate the moment of inertia value. Here it is a rectangular section. So the rectangular section moment of inertia value formula is equal to I equal to B dq by 12. The breadth value is 60 into depth value is 35 cube divided by 12. That is 214375 mm power 4. So the moment of inertia will be represented by a symbol I. The unit will be mm power 4 or centimeter power 4 or meter power 4. So the unit has to be in terms of power 4. Next, we will calculate the Y value to maximum bending moment. Maximum bending moment will be occur at the center of the beam. The center of the beam will be the neutral axis. So Y equal to 35 divided by 12, that is 17.5 mm. So Y equal to 35 by 2, that is 17.5 mm. So we has been calculated the Y value. So and I value. So we has been calculated all the three values. So sigma B equal to 3.75 into 10 power 6, followed by I equal to 214375, followed by Y equal to 17.5. So sigma B equal to 306.12 Newton per mm square will be the bending stress variations. So the bending stress variation will be like this. If it is a rectangular member, the bending stress variation will be a triangular variations. So the triangular variations will be like this. So we has been calculated the sigma B value, that is bending stress value will be 306.12 Newton per mm square. So next we will go through the another sum with UDL loading condition. On previous question we has been gone through the variation for a point load. On previous question, we has been seeing the variation for a point load. Followed by this question, we will carry out the variation for a UDL member, another type of load. In this question, here it is a rectangular member. The rectangular timber beam of span 6 meter and the cross section will be 200 by 400 mm, is freely supported at its end, carries a UDL of 10 kilonewton per meter, runs off entire span a concentrated load of 12 kilonewton at center. Find the maximum bending stress and draw the bending stress variations. So according to this question, we has drawn the simply supported beam with the entire span UDL of 10 kilonewton per meter along with the central point load of 12 kilonewton, with its breadth value will be breadth or width value will be B equal to 200 mm and depth equal to 400 mm. So we has been drawn the cross section along with its bending stress variation sigma B. So that is bending stress variation will be always like this, irrespective to any cross section. If you are converting a cross section from rectangular to circular or square or T section or I section, yeah, whatever may be the cross section, the bending stress diagram will be tendence to remain same always like this as a will be a triangular variation, zigzag triangular variation. It will be uniformity for all the irregular cross sections or regular cross sections. So we will calculate the bending stress for a UDL. So for that purpose, we will calculate the reactions initially. So that is, this will be RA and this will be RC and this will be B point. So in order to calculate the bending moment, we want to find the reactions. So reactions is, that is RC will be traveled in this point to reach that. So RC into 6. Next followed by UDL will travel in this direction to reach this, followed by point load will also travel in this direction to reach the A point. So that is RC into 6, that is equal to 6, that is 10 into 6 will be the distance. So half of the distance will be 6 by 2 plus point load will be 12 into 3. So from this we has been calculated RC equal to 36 kilonewton. Next, according to the equilibrium condition, summation V equal to 0, by applying the equilibrium condition, summation V equal to 0, we has been known that RA plus RC equal to 10 into 6, that is load into distance, plus point load 12 kilonewton, total is 72. So we has been previously calculated RC equal to 36 kilonewton. So RA equal to 36 kilonewton. From the observation, we has been calculated that RA equal to RC equal to 36 kilonewton. So next will be, we know that bending, according to the theory of simple bending, M by I equal to sigma B by Y. So from this relationship, we has been calculated sigma B equal to M by I into Y. So we want to find all the three values one by one according to the cross section. So first thing we will calculate the moment of resistance M value. So for that we has been calculated the reactions. So next, in order to calculate the maximum bending moment, so the maximum bending moment will be occurred at the center. So the maximum bending moment will be occurred at the center. So we want to transform all the force to the center B point. So that is RC into 3 will be 36 into 3, that is 108 kilonewton. 108 kilonewton will be transformed into 10 power 3 as a Newton. Meter will be transformed into mm with the help of 10 power 3. So 108 into 10 power 6 Newton mm. So we has been calculate the moment value. Next, we will calculate the moment of inertia value, I value. So moment of inertia I equal to B dq by 12. We know the cross section. The cross section is 200 will be the breadth value. 200 will be the breadth value, followed by 400 will be the depth value. So 200 into 400 cube divided by 12. So the moment of inertia value will be 10.667 into 10 power 8 mm power 4. So the moment of inertia value has been calculated. Next will be depth value. Depth equal, that is y equal to d by 2. D will be 400. So half of the 400 will be 200 mm. So m by I equal to sigma b by y. So next will be that by substituting all these values, we has been acquired the value of bending will be 20.55 Newton per mm square. So this will be the variation of bending stress along the top chord as well as bottom chord. So the value will be 20.55 Newton per mm square at the top as well as bottom. 20.55 Newton per mm square. So at the bottom will be also the same value, will be 20.5. 20.5 Newton per mm square. So we has been discussed that the bending stress variation will be at a linearly triangular variation. The shape will be tendance to be the retained as a same irrespective to any cross section. If you are changed from rectangular to circular, or it may be circular to triangular, or it may be circular to T section, whatever may be the section, the variation will not gets varied. It will be it will be remains at its the original irregular, that is a triangular shape. Next, another one important topic is that we will calculate the shear stress variations. So shear stress variations will be carried out for the member with respect to the cross sections, because the shear stress variation has been deviated for member to member. If it is a rectangle, just we will go through one example. If it is a rectangular member, the shape will be like this. If it is a I section, the shape will be like this. If it is a triangular member, the shape will be like this. So the diagram indicates that if the shape of the member will has been varied, according to that the shear stress variation will also gets varied according to the situation. So next will be that from the standardized one, we will calculate the shear stress variation. The shear stress variation will be like this, and at the exterior end, the shear stress variation will be 0. Shear stress variation will be 0 because on that location we has been known that bending stress variation will be maximum. So the maximum bend sigma b will be maximum. So if the sigma b will reaches its maximum value, that on that location the shear stress value will tendence to be a 0. Here the shear stress value will be 0. On this location, the bending stress variation has been, on this location the bending stress variation will be maximum. So which is directly, that is which is indirectly proportional. If the bending stress value reaches to maximum level, the shear stress value will tendence to a minimum level. Similarly, if the shear stress value reaches its maximum level, the bending stress value will tendence to be a minimum value. So these are the direct variation between the bending stress and shear stress, and bending stress will be always tendance to remain in this shape, but the shear stress variation will get varied according to the situations. If it is a rectangular, the shape will be like this. If it is a T section, the shape will be like this. If it is a circular, the shape will be like this. So it is which has a direct relationship with the shear stress. And we will go through the maximum shear stress Q max equal to 3 by 2 times of Q average, or Q max equal to 1.5 times of Q average. That will be an important formula, because in order to calculate the maximum shear stress, Q average equal to 1.5 times of, that is Q max equal to 1.5 times of Q average. So it is a important parameter for the shear stress variation. So if it is a triangular member, the Q max will be lies at the neutral axis, and similarly at the neutral axis we will obtain the maximum shear stress. We will obtain the maximum shear stress, and we will go through the shear stress on the upcoming classes by the detailed sum. If we are obtaining the calculations, we will predict the answers and we will draw the shear stress variations. Thank you all.